So good morning, everyone. So, so thanks for having me for yet another session. And today I'm going to talk about scaling laws, right? So, what exactly we will look into it? What exactly is scaling law? Again, not something that's to understand the scaling law is not something that's quite rocket science, but is something that these laws exist or apparently exists is something that is quite surprising, and not much of that this has been explained so far, so it's quite interesting. So we are going to delve into all these different types of scaling laws, and we are going to see why they are important, right? So that's the idea. Okay, so again, sort of a recap or a context to motivate the today's talk. As you can see, starting from 2018 onwards, models are becoming really large, and but then something started happening. It's kind of like almost like trend coming back. So from 2022, you're seeing two strands or two threads coming in. One which is sort of research that is again moving towards smaller models, and and of course there's another strand which is moving towards even larger models, right? So we don't know at the end of the day where we would lean more towards, but probably this today's talk about scaling laws will help you to understand uh, what are the nuances when we have to decide which one of these directions we should be investing more time on in terms of a researcher, also in terms of a ML engineer, if you have to choose that sort of a career. So emergent abilities in LLM, right? So what exactly, let's try to understand what exactly we mean by emergent. Okay. Uh, so in this famous GPT-3 paper, which you probably would know, it was a GPT-2 paper rather. It was shown that there were two things that came out from the experiments that were discussed in that paper. The first sort of understanding was that LLMs are few shot learners. By few shot, you would mean that, okay, if you don't give an LLM a prompt, and if you just by no prompt, what it would mean is that you're not giving any prompt and you're asking the LLM to execute that task. Say a task of summarization. So you're just asking the LLM you're putting a document and you're asking the LLM to summarize that document. That would be like no prompt. You're just giving the input and asking for the output. But one shot and few shot would mean that you're also giving certain number of examples. So you're saying that, okay, if this is the document, then this is the summary. If this is the document, then this is the summary. If this is the document, then this is the summary. Now tell me, if I give you this document, what would be the summary? So you're sort of like helping the model to understand the mapping between the input and the output within the prompt itself. And by by one or few would mean what? Would mean how many number of such examples or such pairs, demonstration pairs you are giving, right? So one shot would be that you only give one example, and then you ask the model to give you the output. Now, of course, it's quite clear that the more help the model gets, the more the model is able to would you would expect that to happen, rather, that if you give more help, if you guide the model more, it would be able to give you better results. And what happens is that as you give the number of examples, as you increase the number of examples, you'll see that the accuracy keeps climbing up, right? But then something also happens at the same time. If you look at it very carefully, you'll see that this phenomena of improving the performance exists only when you climb up to larger models or models with more parameters, right? And then only you will see that, okay, so so if I see so as I look into, so this is the jump, right? So this jump, I'm happening to see this jump, right? So with 13 billion parameters, as you climb up to 175 billion parameters, you see suddenly that there is a jump in terms of the performance, right? So so that's the thing. Even in even with very smaller, let's say just one shot, right? Even there you see that there is sort of a jump in terms of the accuracy, right? So that's what we mean by larger is better. Okay, so as you increase the size of the model, you will certainly see these jumps happening. Okay, so this particular task was a task to remove random symbols from a word. So that was the task, and we also try to understand what happens when we try to do some arithmetic tasks, give some arithmetic tasks as well. So these are all different types of arithmetic tasks. You see two-digit addition, two-digit subtraction, and so on and so forth. And again over here you see this sudden jump, so like as an example, you see there's sudden spikes. So there's sudden spikes, right? For a given model, you see these sudden spikes. So these spikes are sudden. So this is to be understood. Okay. And one more thing, just a little bit of digression, is that you see that these spikes are you are achieving these spikes a lot earlier when the task is relatively easier as compared to more difficult tasks. Let's say this versus this. Let's say 4-digit addition versus 2-digit addition, right? So in a 4-digit addition, you need to go even beyond, in terms of the size in order to get that spike. So what I mean to say is that, and it's intuitive, like if the task is harder, you would have to push the size of the model more in order to get to see that spike. If the task is easier, you get to see that spike a lot early on, with not that much of scale required. So that's the point that I'm trying to make over here. Okay. So some more examples. So this is basically some examples of in terms of some like this one is the arithmetic versus the language understanding. This is the MMLU benchmark. So this has a lot of different types of challenges or tasks, and all related to language understanding. And over there also, this paper, what they did was it looked into, at that time, it looked into one of the larger models, Gopher, and looked into GPT-3, and it tried to understand to what extent these spikes are being seen. Okay, so these spikes are being seen, right? And something very interesting over here, the point that I want to make here is that the discussion is not about which model is better than which model. So try to make that clear. I want to make that clear. The discussion over here is the spikes, this sudden jump. And irrespective of what they are trying to say over here is that irrespective of which model you look at, if you keep on increasing you scale the model, you'll suddenly get to see this spike at some point, right? And quite interestingly, you'll see that in all these experiments, there is a range which happens to be between 10 billion and 100 billion parameters, where you're suddenly seeing this huge spike. So if you look at the previous, so it's around that 10 to 100 billion where you see that spike coming up, right? So by the way, note this down. We will need it. So in our discussion down the line. And again, for a task like program synthesis, you again see this spike somewhere a bit later than 100 billion for program synthesis. So that's the thing. So these are some NLP tasks. And again, you see the same thing happening, the spikes. Coming up, right? So as you increase the parameter. So now we looked into roughly we could understand that, okay, all right, so there's some sort of sudden performance increase as we keep increasing the number of parameters of the model. What if we also increase the number of training steps, or we can also count in terms of the flops or the floating point operations? What if we increase the number of trainings, the training time or the training compute? Can we also see the flop, see the spike over there as well? And the answer was yes. And they actually looked into different types of model, and then they figured out that, yeah, for different tasks and for different models, you are again seeing the spike as you increase the training. As you increase the training, you are again seeing this spike, noticing this spike for different types of tasks, right? So it's also, so given a particular model, which means if you fix a particular model and if you keep on increasing the training on the compute, you can also expect to see the spike after some time, right? Which you were not initially seeing. So these were some of the early observations. And then what Google did was that they came up with this big benchmark. Again, that's another benchmark for which consists of lots of different types of AI challenges for evaluating large language models. And what they did was they said that, okay, so we will try to quantify this emergence or this spike. So can we quantify the spike, in the sense of how much is this spike? So they came up with this measure to quantify the spike for a given model, right? And what they did was they said that, okay, all right, let me take for a particular I, where I is a particular size of a given model, right? And let me take the prediction, the score rather, or rather the prediction, the score given to the prediction. And let me look at the max of all. So whatever was the maximum score that particular model got, and let me look at the minimum score that that particular model got. So which means I'm trying to figure out in this uh, in this in this x-axis, I'm trying to figure out where it got the maximum score and where it got the minimum score, right? So at what point did it get the maximum score and what point did it get the minimum score? And then what I am doing is I'm looking at what is that index or what is that point where it got the maximum and the minimum. And ideally, if it is actually showing emergence, then the minimum would be, the point where it got the minimum would be less than the point where it got the maximum, because you are monotonically increasing, right? So if that's happening, then you are trying to understand that, okay, if that is happening, which means if that is positive, and that is why they did this argmax to figure out whether it's not the other way around. So it could have been the other way around also, which means somewhere early on you are getting that max, and then later on the accuracy is dropping. That should not happen. So the expectation from this part is that it should be positive. Okay, so that's why you're looking at the sign, right? And then you are normalizing this in terms of how much is that difference, from a median scale point of view. So what is the median difference between that particular y, which gave you that that particular y, for every interval rather. So, and the previous y, basically, so which is the previous the score that you got in the previous point on the x-axis, right? So how much is that difference at a median level, right? So that's what you're doing, and you're doing a square root of the square of the median. So this is what they came up with, emergence score, and they this is a way to understand to what extent models are showing this emergent ability. Now over here I want to clarify something before I move on, is when I say emergent ability, there are two words that you need to be carefully understanding. Your understanding needs to be clear over here. One is, when we talk about emergent, we don't mean that this capability or this ability was completely absent in smaller models. That's not the meaning. The meaning of emergence is, in very loose word, what we were calling as spike. So it's not that the ability is not there in the smaller models. It's just that you are suddenly getting this abrupt sudden jump in terms of the accuracy. That's what we mean by emergent. Okay, so don't think that emergent would always necessarily mean that the capability was completely absent in the smaller models and then suddenly you are getting to see something. So that's not the point. The second point is the ability. Now, when we talk about ability, most of the time when it comes to scaling laws, in the context of scaling laws, most of the time you'll be talking about in-context learning, which you would learn in subsequent sessions. So we call it ICL, or in-context learning. So most of the time the context is this. So which in other words, when you loosely talk with people in this community, machine learning community, about scaling laws, usually people might have in their mind that you are talking about in-context learning. Like, what is in-context learning? In-context learning basically means that you ask the model in your prompt, you ask the model to do something that the model was never trained on, and the model is still able to do something. Loosely speaking, if the model was trained on, I'm just giving you an analogy because I love analogies. So if the model is trained to make chai, and you are prompting it to make coffee, tell me how to make coffee, then the model is still able to tell you how to make coffee simply because of the fact that the model has been able to, at a latent level, the model has been able to associate hot beverage with boiling water, with other kind of processes of making the chai at a latent concept level. And also, because it was trained on other tasks, it was able to also club together coffee and chai within one latent concept, right? So that's why it was able to, give you the answer of how to make coffee. Of course, the tasks, that the unknown tasks, so-called unknown tasks that you are asking the model to do, has to be within one of the known classes of problem. Like, if you train the model to do how to make chai, and if you now teach me how to play cricket, that won't work. Okay, so just a loose analogy. So by ability, what usually would mean is in context learning, but at the same time, it may not necessarily have to be unknown tasks all the time. Okay. All right. So what people started realizing is, when it comes to the scale or scaling models, there are three factors in which people can actually scale. One, and where you can start getting to see the spikes. So the spikes can be observed in terms of scaling the amount of training data. It can be seen in terms of scaling the model size, which we saw in the previous examples, and it can also be in terms of scaling the amount of compute, or the training time, or the training resource, or the training steps, which we also saw, like flops in the previous example, right? And what exactly is a flop? So a training compute can be measured in terms of flop, which is basically some constant alpha, in terms of which would be the number of basic operations that you would do to do some sort of matrix multiplication and addition. And it turns out to be that both the forward pass and the backward pass would mean roughly six such operations or flops, and multiplied by the model size, multiplied by the training data, would come down to the overall total flop. So that's how they are related in a flop sense. So one important thing to note here is that there should not be, when you are trying to understand how models would behave as you scale one of these, you have to understand that the model should not run out of the other two parameters which are needed for doing the first experiment. As an example, if you have to figure out, let's say you want to do an experiment on a particular model and see that if I keep increasing the training data, what happens to the accuracy. So the assumption over here is that, okay, let's do that experiment, but during the course of that experiment, if you feel that you need more amount of bigger models to figure out whether that spike is happening, and you are going to get that. So which means the model size is not a constraint. Or if you want bigger, more amount of compute, then you will get that compute. That's not a constraint. So that's what we mean by no bottleneck. Or if you want to do it across model size, let's say now you want to experiment over the model size, like as you scale over the model size, then if you need more data, more records or training data in order to see whether there is something like that, the assumption is that you will get that training data. There is no dearth of training data. There's plenty of supply of training data. So that's what we mean by, if you fix one parameter, then the other two parameters should not be a bottleneck to run that experiment, in order to conduct that experiment, in order to figure out whether there is actually that spike happening or not. Right? So that's the idea. Okay. Some recap of so basically, so this is the you have already probably, not probably, but you have already discussed these things in terms of, at least in terms of the parameters. So you have the embedding matrix. So that would consist of the vocabulary matrix, which contains all the vocabularies, and the context. So this is the context length, which means the sequence, the input sequence, basically nothing other than the input sequence. So how big is that sequence that you are feeding to, let's say, a transformer kind of model or an LSTM or whatever that is. So, and this is the dimension. So that this plus this multiplied by the dimension, that's your embedding matrix size. And then attention would be this, because the 3 comes because you have Q and A and B. So that's how you can compute the number, or you can calculate the number of parameters required for attention. Masking, nothing. Projection, if you want to do the projection, then this many number of parameters are needed. Feed forward, because it's layered, your model is layered, so between 2 layers you have a sandwiched feed forward network, like a 1 layer or 2 layer feed forward network, right? So that would again have that many, because there are 2 layers, one layer which is the input layer and the hidden layer. So 2 multiplied by that many numbers. So DFF is the dimension of the feed forward network that is sandwiched between 2 attention network layers. Got the point? Are you remembering the architecture? Okay. And then if you add them, all of them up, then that would be the total embedding. Similarly for flops, so this is how you would calculate the flops. I'm not going to go into the details, but usually people look at it not from a flop point of view, but from a PF day point of view, like beta flop day sort of. And that is basically 24 hours multiplied by this many number of seconds multiplied by this, which is equivalent to saying that it's basically this many number of floating point operations, right? Okay. So emergent abilities. So till some point, people were thinking that we could never predict when that spike will happen. When that sudden spike will, you keep doing and you cross your finger, and at some point you will suddenly start seeing that thing. So basically the notion till a good amount of time was that, well, these emergent abilities are unpredictable. You can't really foresee them, right? So now if that's true, then there's a problem. As Homo sapiens, we love to predict, right? We are very uncomfortable if we have uncertain situations. So the problem is that we would never get to know which abilities are really triggering and when are they going to trigger, right? If it is truly uncertain, then we will never get to answer the first question, which is a very important question. What controls trigger? That's even bigger and I would say tougher question, which is the explainability part of it. Can we make desirable abilities to emerge faster? That is where all the smaller language model research is sort of going, in that direction. So if we can know that these are the desirable abilities, and if they emerge at this certain point, can we bring it to an earlier point? Right? So can we do that? Can we make undesirable abilities to be suppressed? And when I was preparing the slide, it just occurred that this the California AI Act just came up. So it's very pertinent to this fourth point, which is if you are not seeing an undesirable ability right now, and you think that, oh, that's fine, and you are opening the project or making the project open source or launching the model. But what happens if somebody starts scaling that same model just by increasing the number of parameters or something, or the number of amount of training data, and then suddenly the Pandora's box is open? So what happens about that? Can we have ways to control that thing beforehand, sort of, right? So that's And if it is uncertain, we can never do that. If somebody proves, let's say somebody proves to you mathematically or empirically in some way that this is really uncertain, then we can never ever even, there's no way to actually do this. So some other values of the scaling laws is that how much return that, you can do budgeting. So there is a budgeting value to scaling laws. Like if you are a machine learning ML ops sort of a person in a company, you would really want to make everything be predictable. Because if it is not predictable, you will not be able to budget anything. As an example, the return that you would get given a particular compute, or if you have a limited compute budget, then how do you balance between the model size versus the data set size? Because both can give you that jump, right? So which one to grow more, which one to grow less, and how do you manage it, given that your boss has told you that this is what you will get, this is the amount of compute resources that you're going to get. Now how do you do those adjustments? So the question is that people started dabbling about it, after these observations were seen, was that can there be a curve that we can fit? In other words, can we fit emergence, right? So is it really unpredictable, or can we predict it? By fitting a curve, it would mean that we can predict it, right? So see, the intuition is quite clear, which you might have gotten even from your basic statistics 101 sort of a class. And over there, let's say that you have an input that x1 through xn. Let's say that then, and that draws from a distribution, a normal distribution, or that with a parameter which is parameterized with the parameter mu and sigma square, which is the mean and the variance. And let's say the task is that you have to estimate the average as in terms of the estimating the mu, and that would be basically summation of xi by n, given that that's a population. So what's the error? So the error usually, the expected error is basically this, right? So this is the expected error, and this error is nothing more than sigma square by n, right? So that's the expected deviance or expected error, right? And if you do a log, if you take the log on this side and the log on this side, so you get this. So the log of the error is basically minus log n plus 2 times log of some sigma, right? So in other words, if you want to look at it, it's basically that it's already a power. It's already a power law. Why is it a power law? Because if you do a log of the power law, then you would get a linear thing. Log means on the y you make a log of the y, you make a log of the x, and you get a linear equation in terms of the log. So the y-axis would also, you would do a log on the y, you would do a log on the x, and then the power law would suddenly become a linear equation. So that's the general intuition, right? So which means that it's not that errors would actually follow a power law. So if errors are following a power law, which means loss, right? So error means loss. So if loss can follow a power law, which means inversely the accuracy also follows a power law. So that's the idea. So if loss drops according to a power law, then accuracy will go up according to a power law, right? So that's the intuition. In a non-parametric setting, which means you don't have mu or sigma to a specific mu or sigma to begin with, then also there are one very interesting technique is that you just cut. Let's say that in a 2D space, you just cut the boxes with, let's say, this sort of a this sort of a, you know, sort of something like this in like its box, right? So and so the with the length of this, and what's and if you do that, then you start getting this many number of boxes, and each box contains this many number of samples. So the error then becomes per box would become would approximate to 1 by root n plus some other smoothness terms. And if it is d dimension, so this is for 2 dimension, so if it is d dimension, then it would be, instead of n raised, so it would be n something like this, right? So so that's the thing. So, or in other words, so this is this non-parametric version of looking at the same thing, or the intuition which we talked about, right? So the idea is that there will be a power law. That's number one. What's the takeaway? The takeaway two is that there is some power which depends upon d, or the dimension. So the exponentiation of the power law would sort of depend upon the dimension that that on which the data point is. So the data point's dimension, right, or the training data's dimension. Okay, so so this was the thing. Like, what if the loss drop or the emergence follows a power law? So a power law again would be something like y is equals to a into x raised k, where k can be negative. So which means something like the loss over a particular parameter x is inversely proportional to x raised alpha x, where alpha is a function over the dimension, as we just said, right? So as we know, we discussed that there are three major factors, right? One is the parameter size, one is the training data, and one is the compute. So let's look at the parameter size. So they came up with this hypothesis. This is a hypothesis, okay? So this is just a hypothesis. So they came up with this hypothesis that ln is approximately some scaling factor, which is a constant. This is a scaling factor, a constant, upon the n. This n is the model size on which you want to do that experiment, the x-axis, right? So the n is the x-axis basically, and it turns out to be, through empirical evidences, as they started fitting the curve, it turned out to be that nc is this value and alpha n is this value, right? So that these are the two knobs, so to say, that controls the scaling. One is the exponentiation and one is the scaling factor. So these are the two controls. These are the two knobs that control to what extent it will shoot up and show that emergence, right? So similarly, you have the amount of training data as the other parameter, and they said that if we also try to understand what's the effect of increasing the amount of training data independently, independently means by fixing the amount of parameter, which is n. So if we fix the n, if we fix the compute, and then if we keep on increasing the training data, what really goes on in terms of the scale, right? And that also they came up with a very similar, it's just that the constants are different. The constants will be different because the parameters are different, right? So they came up with this particular hypothesis, which is a power law by itself. One important thing that we have to understand over here is they did not take the embedding matrix, so no embedding matrix during the calculations or the curve fitting. And over here, by training data, what they really mean is the total number of tokens inside the training data. Okay, so the total number of tokens inside the training data. So let's say that if the training data consists of only one sentence, imagine, and the sentence is John loves ice cream made in New York. So John is one token, loves is one token, if that is the tokenization method. So this constant DC is also dependent upon the scaling factor, also depends upon then the tokenization method. Because if you do a tokenization like a BP, sort of a subword based BP tokenization, or some other kind of tokenization, right, then the constant will change. So it depends upon, it's a function of the tokenization method. So it depends on the tokenization method. Okay, so that's the way we would measure the scale, which is tokens. And then we have the compute. That's the third factor, right? So again, the same sort of same sort of equation, and we will see that we are measuring compute in terms of in terms of loose C, which is the actual compute that you would require, and also in terms of C min. So I'll tell you in a minute what is the difference between C and C min is. C min is the minimum amount of compute that's required to achieve a target loss. So let's say that you fix the loss and you say that this much, the loss cannot be greater than this, it has to be this, let's say. Then what is the minimum compute that you will require, the minimum number of flops that you would require in the training, the iterations, that minimum number of flops that you would require to achieve, to hit that that loss. So that is C min. Okay, so and again, as you know, that this is measured in terms of PF days. So it's basically that constant multiplied by 24 hours multiplied by 3600 seconds, right? So that's the total number of PF days or petaflop days. Okay, so so these three fundamental laws were proposed by a group from Johns Hopkins and OpenAI, and Kaplan was one of this group, and it's commonly known as Kaplan laws. And the paper is was published in 2020, and it's in Argzev. So it's not really published in any particular, but it's hugely cited paper. So this was what was the foundation, the first. I wouldn't say the first scaling law. There were scaling laws before this as well. So let's say in 2017, there were certain kind of scaling laws that came up for LSTM kind of models and so on and so forth. But a rigorous, thorough empirical analysis, probably this was the first paper that we can see. Okay, so for the compute a more reliable version, this is just a nitty-gritty. The more reliable version is the C minimum version. That's more reliable. And what C minimum is? So C minimum is you take the compute, and then what you do is you take the batch that's the minimum or the most critical batch to achieve this loss. And then what you do is so this is the formula for B critical. So how do you get that B critical? So the batch critical, okay, by batch I mean the training batch. So how many number of records you're packing into one pass, sort of. So that's the batch, and it has this constant of 2 multiplied by 10 raised 8 tokens with this alpha B. So that's the batch. And for any particular L, so if if you plug in the L, let's say this is the loss that you are looking at, you will get the corresponding B critical. If you plug a different L, you will get the corresponding B critical. So you can actually get all the B criticals at different loss points, right? Now you plug this particular L, get the B critical, look at the particular batch that you are using in your experiment. That ratio, together with the compute that you are using up, would give you the C minimum, which means that would give the minimum compute that you would have required. What it means is that you might be using something more than what the minimum is in your experiments. So more reliable is to actually look at the threshold, the minimum compute, and then see how that scales, as opposed to the compute that you have started to use. So you could have used one compute and then you could have run that experiment. So what they're saying is that don't do that. Whatever compute you are using, get the C-min of that compute and then scale according to C-min instead of according to the C. So there is the C, which that is increasing across x-axis. You take the corresponding C-min and see how the C-min is increasing across the x-axis. That's what it means. Okay. And so that's the thing. So basically, this is the usual C, where the compute is C. You convert that into C-min. So get that converted into a C-min. So instead of infinite amount of data, you calculate the d-opt, the optimal amount of data, and instead of a fixed batch size, you take a B that is lot less than the critical B. Now this is a bit, again, a little nitty-gritty, but this is important. Why? Because what people have seen, earlier results have shown that if you increase the batch size above the critical batch that achieves that loss, you will get diminishing return. It actually goes down. The accuracy starts going down. So if you increase the batch size beyond that limit, beyond that threshold of B critical, the loss actually goes down. So what they are trying to say is that if you really want to see how compute, what kind of spike effect compute has, keep your batch size within that limit. That's what they are recommending. That keep your batch size within that limit. Don't go beyond that limit. That's what they are saying. Okay. All right. So it turns out that we are in luck. This was just all these laws, so-called quote-unquote laws, they were just predictions. They were like hypotheses, right? That, well, this is how it would look like. It just turns out that when they actually do those experiments, they started getting to see that actually the model was literally sticking to that line. Why is it a straight line? Again, just to remind you, because it's log-log. So that's why, it is going down. The loss is going down as a straight line. And ideally, it should just follow that straight line. The real empirical results should follow that straight line. If it is following that straight line, then it means bingo, we have gotten the power law, which means actually models are following the power law. And in reality, when we really do the experiments, we are seeing that the models, with a little bit of minor deviations here and there, but the models are actually, they are following that. They're moving across that line, right? As you increase the parameters. Similarly, for the data size in terms of tokens, again, the same thing is going on, except for some early deviation, but it's more or less follows that, right? And over here also, this is more reliable because the deviation is less as compared to here, but you could have done both ways. It's just again an integrity, whether you want to do C min way or whether you want to do the C way, but it's just the C min gives you a better prediction. So that's the thing. One important thing to understand: when this paper got out, the largest scale reported scale was 1 billion versus 100 billion, which we were seeing in the earlier experiments in GPT-3 and GPT-2 and all. So, which means what? That they must have done the fingers crossing thing, that okay, it will remain so even if you go to 100 billion, it will still follow that line. It won't deviate away from that line, right? So as you go towards 100 billion, even if you cross 100 billion, even if it is 500 billion, it will still follow that line. It will still go down and follow the same line, right? That is the finger crossing thing over here, which means it's not a mathematical analysis as such. It's not a mathematical bound or a guarantee or anything that, oh yeah, we have finally found out that this is how models will work. No, that's not something. It's an empirical result. So it's an empirical curve fitting that, okay, yeah, it follows this. And we think that aage bhi aisa hoga. It will keep on following the same thing. Okay. Okay, so then what they did was they started to dig a little bit deeper and try to understand that what else is going on in this as we scale. Let's say, so what they did was they said that, okay, all right, so if we keep scaling the parameters and we don't supply the amount of training data, like bigger models, what is the intuition? That bigger models will love to eat more data, more training data in order to perform. But let's say we don't supply that data. We don't supply that amount of food for the bigger models. What will happen? And what they saw was, not surprisingly, that it just saturates and doesn't go, the loss doesn't drop much. It just gets plateaued. It just gets saturated. So it doesn't matter even if you're increasing the model size, if your training data doesn't increase, so it doesn't matter how big is your model, the loss is not going to, it's going to be the same as smaller models. So your bigger model will perform the same way as a smaller model. So nothing really will happen. So that's a big observation, really. Which means that your bigger model will just overfit and sort of like memorize everything, memorize your training data, and won't be able to generalize well. And that's why the loss, you're not getting to see that much of drop in the loss. So as you increase the data size in terms of tokens, as you increase the data size, then only you see at this point, you start seeing again, it starts following that power law. So as you keep increasing data size, you will see that then slowly it's again coming back to that straight line, and again it's pushing itself back into the track, right? So that's the thing. So this is so basically this is what we call as the bottleneck. So if there is a data bottleneck, which means there is not enough supply of data set, you have run out of your training data, then it doesn't make sense. Okay, there's no point increasing. So this is the corresponding overfitting that's happening, and the overfitting will happen very quickly for larger models if your data set is small, right? So this is the ratio between the model size, the model scale, how much you are scaling the model, keeping the data set fixed, so that and you will see that it steeply rises for everybody, Okay, all right. So this is called this was termed as the universality of overfitting. Why universal? Because it doesn't matter which model. It doesn't matter what is the data size that you are increasing. You are bound to fall into this trap of overfitting if you don't increase the data set, right? The other thing that they saw was this now switched the role. So they took now data set and fixed the model. So let's say that, okay, so let's do the opposite experiment. So let's fix the model. Let's take a small model, but let's now keep increasing the training data. Now, will the small model suddenly start showing emergence, quote unquote, in terms of the spike? Can the smaller model show the spike? Like suddenly, as you increase the training data, suddenly the smaller model becomes immensely intelligent, sort of. Can that happen? And the answer is, again, no, it's not happening. So it only happens as you increase the model size. Then only you'll get to see somewhere over here, like 0.5. This is like 0.5 billion, a bit 0.71 billion, and you sort of get to see that something closer to the power law. You start getting to see, not before that, right? So it's also not that you can keep increasing the training data and any model, any small model can suddenly start showing you that emergence. Not going to happen. So what does that mean? It means that you have to increase both. You can't simply fix one and increase the other. You have to increase both in tandem. So that's the first takeaway, that both parameter and dataset needs to be scaled, right? So the power law cannot be just this or cannot be just this. The power law has to be some combination of these two. And then only you can fit it properly. Then only you can actually show that, yeah, this is reality. This is how actually the models are scaling. So you can't just take this or this. So that is why the joint scaling law was proposed. And that looks something like this. Okay? So the idea is that, and what Kaplan and others, what they showed was that the relationship between the data and the data scale and the parameter scale is this. This is the relationship between the data scale and the parameter scale. And empirically, that scale turned out to be somewhere around this. So in other words, if you increase the model, if you want to increase the model 8 times, the model size, you increase the model size 8 times, you have to increase the model at least 5 times. Sorry, the data. You have to increase the data set by 5 times. So you cannot just keep quiet on the data point on the data side. If you increase the model 8 times, you have to increase the data set also 5 times. So that's the relationship. 8 times over here, which would mean 5 times of the data set. Then only you can see the spike. Then only you will be able to follow the power law. Not just the spike, but you will also be able to follow the power law. Otherwise, your model will not follow the power law. Okay, and things won't be predictable. So that's the point. Okay. What's the second observation? They also saw that if now what they did was they said that, okay, all right, if we scale the parameters now, but now I am going to pitch the parameter against the compute. Earlier, I was pitching the parameter against the data set. So now I'm going to pitch the parameter against the compute. And as I increase the compute, then only at this level, I'm going to see something like the power law, which means that if my compute is low, then I will not be, in fact, I will be seeing some ajib things, some very strange things happening. In other words, as I increase it a little bit, it actually goes up. The loss actually is going up. So it's only when I have enough, the minimum amount of power, compute, which means I allow that much of compute to happen, or which means my manager allows me to actually go through that much of compute and doesn't want me to ship the model as it is, then only I will see something like this to happen. Okay, so you better, your first thing when you go to the corporate is to teach your manager scaling laws. Okay, that's important for the management, for the boss, for the co-founder, founder, whoever that is. Okay, so extremely important, or the product manager. Okay, so this is the thing. Now, a very different way of seeing the same thing is performance versus steps. So now we are looking at the same thing, but we are looking at it from the training steps point of view instead of flop, but just the number of iterations, the number of steps, right? Passes, the number of passes. And that again, as you increase the steps, then only you will get to see that the training, the test laws, the test law actually, otherwise it's sort of like saturates and flattens and doesn't decrease much. So it's only with the increases of test steps that you can actually bring it down in terms of the loss. So this observation led to the second key takeaway, which they started calling universality of training, which means what they figured was it's not just good enough to have a joint loss that can characterize parameter and data set. You also need to characterize parameter and the compute, or at least you have to parameterize the yeah, where is it? Okay, yeah. So yeah, so this was there, so this we saw, but this is not good enough, not enough. Okay, you also need to observe this. You also need to have a law that captures the dynamics between these two, right? And again, it pretty much looks the same. SC is again the scaling factor for the number of steps. S minimum is again, the minimum number of steps that you would require to achieve a particular loss point. Okay, the minimum number of training steps. You can think of it like epochs as well that you would need, right? And again, over here, what they are saying is that over here, for some reason, they're saying that, okay, in this particular example, you better keep your, so what they did was, they're not recommending it, but what they did was they actually kept their B lot bigger than the minimum B critical. And then, which means that they are opening the possibility that actually there can be a loss drop, a loss increase, because if you go beyond B critical, if your batch goes beyond B critical, then the loss can deteriorate. So they actually kept that possibility open, and then they started to increase the steps to figure out whether you can again drag it down and bring down the loss. So basically, they started out with a bad situation, and then they tried to figure out whether by increasing the number of training steps, you can bring it down to a good situation, right? So that's the sort of what my interpretation would be. Probably that was the point of keeping the B bigger. And again, B critical as it is, this formula remains the same, and you plug this and then you get the estimate. So basically the idea is that instead of x-axis, instead of keeping S, you're keeping S minimum, and then you are trying to figure out how that scaling is happening, right? And when you do that, you have this alpha S, which is this, which comes down to this value, right? Okay, so very pertinent question. Are we only to worry about these 3 factors? Because there are so many other factors, right? So many. So although not all of the factors have been explored, but certain factors were all explored, and very interestingly, some observations that came out was that the first observation was that the model shape actually doesn't really matter in terms of the depth versus the layers, or the breadth, right? The width versus the depth. So that doesn't really matter much, because if you look at let's say that they started out with the attention head. So let's say the attention head, let's say I increase the number of attention heads, so it's not really giving you that sort of a spike. So there's no real spike as such. If you look at if you try to have a ratio between the number of dimension of the model versus the number of head, and if you keep on increasing that ratio, it's not that you are getting to see. It's weakly. I wouldn't say it's not. It does not matter at all, but I would say it's a very weak association. So it doesn't really matter that much as compared to the other 3 factors. So that's the thing. The other thing is that the aspect ratio, which means you increase the number of, increase or decrease the number of layers, keeping the the dimension of the model the same. And again, you are seeing you're not able to fit it well. So it's increasing, decreasing, and then increasing again. So it's not really something that you would be, able to model well, right? So that was the thing. And this is where they try to play with the dimension of the feed-forward network, keeping the D model the same. And again, that's something that they saw was, the ratio as they saw, it really didn't really matter much. So there's nothing like there's no sharpness as such that, okay, it was, so it's smooth, it's predictable. So there's nothing like there's a sharp emergence. So there's no emergence as such. So if there's no emergence, you can model it, but you can't model it as a power law. So you use power law only when there is a sharp edge, when there is a sharp emergence. So there's no sharp emergence as such, right? Okay, what's the other thing? Well, we said that all these experiments that Kaplan and a group did was on non-embedding, which means they did not take into account the embedding metrics. So then they said that, okay, all right, let's try to do the embedding metrics also. So it's more or less the same, except for a few here and there, maybe this 0 layer, which actually there's a lot of difference between 0 layer versus first layer. But except for that, if you just look at the first layer and this box, you see that there's not really much of a difference, in terms of, if you take it versus if you don't take it, right? So that's what their argument was, that it's pretty much so the point that they are trying to make is that both are showing the scaling law. So since both are showing the scaling law, it doesn't really matter whether you use the non-embedding or use the embedding. In fact, what they probably wanted to show was that that this is maybe this is better in some sense, that what they are saying is that even over here you can see that the layers, till certain point, it's not that they have a lot of difference among themselves. So if you look at the drop between the layers, it's not that there's a lot of loss drop that's going on if you increase the layer. So that's something also that's there. But anyways, I mean, I don't think that there is much difference, according to me, if you ask me. Okay, so there was another a follow-up sort of a paper in 2021, and there was another on the same title, the same. And then what they saw was that even for different types of data sets, they were getting to see the same kind of power law. So the hypothesis is that the composition of the data set also doesn't really matter. Like, you just scale on the parameters of the data set. Doesn't matter what kind of data set it is, it will still show the power law, right? So that was the sort of the hypothesis. This is the summary. These are the joint ones, the joint scaling ones. So yeah, so this is so far so good as far as Kaplan scaling laws are concerned. So is there any other alternative law? So is this the only? Yeah, there were before Kaplan also there were, and after Kaplan also there was something that that became or is becoming very, very popular, and that's a Chinchilla scaling law. So this paper came out in 2022 New Rips. People from these guys were from DeepMind, and they came up with this law. And then they came up with a different sort of a law. They said that, okay, we have these two joint losses to model, and they came up with this sort of a thing that, okay, it's some constant by nt, where t is the total parameters, and these total parameters would also include the embedding matrix that we would see, right? So, and E is the loss that you cannot the loss that is intrinsic to the data set, sort of like the residual, is the noise, and you can't really minimize that any further. So that's the lower, therefore that becomes the lower bound. Okay, so empirically, when they started to understand what this would mean, what this alpha and beta would mean, they came up with this version, and this is the constants involved. So E becomes this, and sort of that way. So, and they also saw something very interesting. They saw that if alpha is, and this is very important to note, they saw that if alpha is somewhere closely similar, is quite similar to beta, then you get the best curve fitting. So this results in the best curve fitting if alpha is equal to beta, right? Which means equal scaling of n and d. So this is something which is a little bit different than what Kaplan proposed. Kaplan said that, okay, if you increase your n by 8 times, your d should increase by 5 times. But these guys, the Chinchilla people, they said that no, it's not like that. You should equally scale. It's not that 8 times versus 5 times. If that is 8 times, this should also be 8 times. If that is 5 times, this should also be 5 times. So that's what is the primary difference. So apart from this sort of things, the scale, and also this is like without the embedding matrix, right? So without the embedding matrix, what Kaplan did, and Chinchilla included the embedding matrix. So nt is equals to ne, the parameters for the embedding matrix, right? And where the embedding matrix itself is basically the vocabulary. This is the vocabulary plus the context together with the dimension. So and this is the compute. Okay, so then a lot of people, I am just showing one results. A lot of people after that started working on Chinchilla, started to revise Chinchilla, trying to figure out to what extent Chinchilla is applicable for, the Chinchilla scaling law is applicable for a lot of these newer models, right? And then, very recently, there's this paper, it's in arXiv right now in 2024 by some people from Epoch AI, the company Epoch AI, and they came out with a revision. So this is Chinchilla, the original Chinchilla by Google DeepMind law, and they came up with this revision. They said that no, this should not be 1.69, this should be 1.82, this should not be this should be this, and this should not be this, but this is a lot higher. So this is where they said that the scaling factor of data set, training data set, is actually a lot higher, and this will give me a better fit. That's it. That's the idea. So that's what they said. Okay, so that's the revision, sort of. That's what they proposed, that we should rather follow this instead of this in order to get a better fit. So it's more about there are a bunch of people who are trying to figure out like who can give a better prediction, sort of. Now, to sort of wrap things up, there's a surprise for all of you, and the surprise is that a very recent paper came up in NeurIPS, 2023, last year, by a group from Stanford, and then they completely made everybody start rethinking the entire problem. It's almost like whether as if like the point of view has changed. And what they said that, okay, we agree that these three factors are important, we are not disagreeing with that, but we did some experiments. So what they did was they said that, okay, let's take only this guy, the model size, and let's try to figure that out, whether there is really that spike, and because of the spike we will need the power law. The power laws come only because of the spike, right? So let's look at that spike. So what they first saw was they saw that, okay, for most of the accuracy measures, so for most of the measures, they are not emergent. So most measures from an emergence score point of view, most measures are not even showing the emergence. It's only a few of the measures that are actually showing that spike. So which means if you are using a different metric for the same thing, let's say same task, the task remains same, but the metric changes, for most of the metrics you don't even see that spike. You only see the spike for just 10%, roughly 10%. So out of 39 matrix, only 4 matrix showed that spike. Okay, so that kind of motivated them to think that whether the devil is in the metric, and it's not, the emergence is not really an intrinsic property of the scale, but the devil is actually in the metric. The devil is actually in the way of looking at it. So they further dig deeper down into that 10%, and then they saw that 76% were all, for the big bench, for the big bench benchmark, they saw that 76% were all multiple choice grade, which means that it's a very strict kind of an accuracy measure, which means you either hit it or you miss it. There is no in between, right? So multiple choice grade means you give an option and you say that, if the highest probability matches this option, then you get an A, else 0. So even if you are the second highest with a very small margin from the highest, still you get a 0. Got the point, the problem? Okay, so it's extremely harsh metric. And then the remaining 16%, so not remaining, but the 16% is exact string match. Again, a very harsh metric. So if the next token prediction, let's say, was supposed to be cat, but for some reason you predicted cats, plural, you will get a 0. Okay, so that's that harsh. All right, and then there was other stuff like blue and normalized aggregate score. So they were all fall under that 10%. So again, first of all, 90% were not even emergent, and then within the remaining 10%, this is the scenario. When they dig deeper into the remaining 10%, then they say that okay, let's relook at the power law, and let's say that okay, so this is your power law, what Kaplan proposed. Okay, C means NC, you can think of it like that, and this alpha, you can look at it like a negative also. If it is negative, then it just reverses, the numerator becomes the denominator. So, and then they equate this with the cross entropy loss, which is the L. This is the L. This was the L. And then they are now trying to look at this from this point of view, from the probability of that token point of view, like how that is equated to this this scale, right? And then what they did was they said that okay, the moment you do that, this becomes an S curve, right? So the accuracy, so over here is the log n in terms of the number, so and then the accuracy becomes like an S curve. And then what they did was they looked into in terms of the length of the token, they looked into the accuracy in terms of the length of the token, and of course if the length is 1, then it's an easier task, but if the length is more, it's a harder task. And that's why if the length is more, you don't get to see that kind of accuracy that early on. You have to wait more to get that kind of accuracy if the length is more. It's very simple, right? So this is the power law, and this is the corresponding S curve when you convert it into this. I mean, it's the same thing basically. Okay, so now what they were saying is that the problem is that most of these measures, which are 1 or 0, are non-linear. And by non-linear, what they mean is that they say that okay, all right, so what they did was they said that okay, let's take this task, the task of adding k digit integers, right? And which means that if all the k plus 1 digit, because it's a k digit addition, so they can be an additional 1 digit. So if the task of that, if the final result, if all the digits match, then only you will get a 1, else you will get a 0, right? And which means that they kind of reformulated the accuracy to be like this. So the probability of single token being correct times or raise the number of tokens, right? So that's the joint probability. So they looked at it from that point of view. And when they looked at it from that point of view, and then when they plotted on in terms of the model, then the shape of this curve looked very similar to what was published. So they came up with this idea that yes, so if I actually take the accuracy to be something which is non-linear, then I get a similar I can reproduce the result, right? That's what they said, that if I do this, then I can reproduce the result. Okay, all right. Then what they did was they said that okay, I am no more interested in exact string match. Let me do something like an edit distance, something like Levenstein or other kind of edit distance. Let me just change the perspective. The moment they did that, then they changed the loss, right? So the loss now becomes something like this. So the moment the loss becomes something like this, you are actually rewarding even intermediary probabilities. So if the probability is 1, which means no loss. If the probability is 0, it means 0. But in in between, if you have, let's say 0.98 or 0.99, you will also get very less penalization. So they did something like that, and then suddenly what happened was that this so-called power law suddenly started looking near linear. Which means that emergence, the so-called emergence, is gone. Is sort of gone. The emergence is gone. Just by changing the accuracy measure. Okay? They did another experiment. They said, okay, all right, now let's look at discontinuous measures which are completely discontinuous, like MCG or multiple choice grade. That's discontinuous, right? And then they said that, okay, all right, if I do the same experiment over a choice of 2, okay, and I am able to replicate what was published. So I'm able to replicate it. So, okay, so far so good. Now let's say that I change it. I change the measure from MCG to Brier score. And by Brier score, again, it's basically this, that you are not, penalizing the intermediary probability with a 0. You're giving some reward. And by doing that, again, what they saw was that this emergence, the so-called emergence that you found, the spike, is again gone. Right? And then what they did, they tried on multiple other things. So they just changed the perspective. And then they tried to understand whether these spikes, whether all these spikes, what happens to those spikes. And what they saw was that that's gone. Sort of gone. So it sort of becomes a near linear scale. Okay? So, and they did it with so this is the so it's, they say that no, it's not a power law. That was their point. The point is that you don't need a power law to explain. You can actually do very well with a near linear counterpart. So that was the thing. And then they started experimenting and they said whether actually it really happens or not in, let's say, some of the latest models like GPT 3.5 and so on. And then they saw that, yeah, something like this is going on, as opposed to this. So then they looked at other big benchmarks and for different types of tasks, and then they said that, okay, all right, so the moment so this was MCG, but the moment they made Brier score, all these spikes went away. All the spikes went away. Right? So basically the key takeaway was that you want to predict without the theatrics, without the drama, that there is an emergence and suddenly it will pop up from nowhere or something like that. They said that you can actually predict. It's nothing like that. You can predict without the theatrics. So you choose a matrix that's basically soft or continuous in some sense. Right? And there's no sudden jump in reality. Most can be predicted on a near linear scale. Okay, if you just change the perspective. And then the big question comes is this: do we really need the power? If there is no, so the power law came because of that sudden jump. So if there is no real sudden jump, then do we really need the power law of scale? And probably the answer is maybe not. Maybe in some cases where you can't have a soft measure, it doesn't make sense to have a soft measure of accuracy, where the accuracy has to be hard. let's say. In that sort of cases, probably yes, but in other kind of cases, no. That's the suggestion. So yeah. So that is what I have for you for today's session.